Schrödinger's cat, both alive and dead, right? Wrong. It's not alive, not dead, not both, and not neither. Confused? You should be, because this thought experiment is pointing to an unsettling and bizarre truth of our universe, which not only is true, but as we will see towards end of this video, is the very base of the life of all living things. A terrifying truth that defies all logic, so much so that Einstein and Schrödinger couldn't accept it. It left even the greatest minds among humans baffled and confused. Forget everything you think you know about the quantum world and let's dive deep into the reality. Here is what you most probably understood wrong. Let's start with a thought experiment, Schrödinger's cat. You put a cat in a box. In it, you have a radioactive atom which decays at random time. The decay triggers a poison, killing the cat. Now you close that lid so no one can see inside the box. And I ask you, what is the state of the cat right now? If you have never heard of quantum mechanics, you will say that there is exactly 50% chance that the atom has decayed and 50% it has not. So there is 50% chance that the cat is either dead or not. However, most people who think they understand quantum mechanics will say that as per quantum mechanics, that atom is neither decayed nor not decayed. It's kind of both at the same time. And therefore, the cat is neither dead nor alive. It's kind of both at the same time. They will tell you this is what's known as quantum superposition. It's like the reality is not decided, and only when you open the box, one of them becomes the reality. But what does it mean that the cat is both alive and dead? How can we say anything about the cat in the box if we don't see it? And most importantly, why does nature care for you seeing it? Well, that's wrong. That's not what quantum superposition means, as per quantum mechanics. It's way profound and satisfactory. Let's go step by step ourselves to find the meaning behind it. To understand this, we have to start with the famous electron double-slit experiment. You have an electron gun and a screen. In between those, you have a block with two slits. You fire electrons one at a time through the two slits. What you expect is a pattern like this on the screen. However, we get an interference pattern like this. Here, most people will say that the reason is this. Electron does not behave like particle but a wave, like a probability wave which passes through both the slits, and then the wave interferes with itself. And then when it finally reaches the screen, the wave collapses and we get the particle. But how come each electron knows where to precisely land so that the whole group of electrons will make this pattern, even though you fire them one at a time? Doesn't that sound weird? Anyway, if you think like this, then you think you understand quantum mechanics, but you don't. You have been taught wrong. So for the next few minutes, I request you to keep everything in your mind to side and let's learn what actually happens. The question here is that which slit did the electron go through? Even though you think you know the answer, let's go rigorously case by case. Let's consider the possibility that maybe all electrons went through slit 1. Even though we know that's wrong, let's test it. How do you test it? Well, you close slit 2 and then redo the experiment. If we get the same original interference pattern, then all the electrons went through slit 1, else no. We do the experiment, we get pattern like this. Most electrons in front of slit 1, which is not same as the interference pattern. That means all the electrons did not go through slit 1. Next, what about slit 2? Let's test that. Open slit 2 again, close slit 1 and redo the experiment. We will get most of the electrons in front of slit 2. This is also not the same as the interference pattern. That means all the electrons did not go through slit 2. What if some electrons went through slit 1 and some through slit 2? How do we test it? Well, if you think this is the combination of previous two tests. So we should get the result as a combination of previous two tests, like this. Some in front of slit 1 and some in front of slit 2, which is also not same as the interference pattern. That means either slit 1 or slit 2 option is also not correct. What else? What if each electron goes through both the slits? Well, how can we test it? If each electron goes through both the slits, so if I bring the screen all the way close to the slits, I should get two dots on the screen, because the screen is all the way near the slits. Think about it. But does that happen? No. When you do the experiment, you will always get only one dot, which means this is also wrong. What now? How about the electrons go through neither of the slits? How do we test it? Well, we close both the slits and redo the experiment. But then we get nothing on the screen. That means this is also wrong. What is the answer then? We actually ran out of options. Well, my friends, this means only one thing, that the electrons go through the slits in a way that we humans can't even conceptualize. That means we can't use our words, sentences, vocabulary, pictures, animations to demonstrate what they are doing. What they are doing is a completely new behavior. And that's why we came up with a new name for it. We called it quantum superposition. We say that the electrons are in a quantum superposition of going through slit 1 and going through slit 2. What does that mean? We cannot express it in literature. We cannot express it without using math. We can only tell what the electron is not doing with words. If we try to explain what it is doing, we will only cause miscommunication. But hang on, so is it wrong to say that the electron go like a wave? Let's clarify this. First, quantum objects like electrons are not literally like the waves shown in the animation. The wave represents the probability of finding it at a certain location. It is not the object itself. But where does this probability wave idea comes from? It comes from the Schrödinger equation. If you look at time-independent Schrödinger equation, in simple terms, it says that the kinetic energy plus the potential energy is equal to the total energy of the quantum system. This Greek letter here is called psi, and it represents the quantum state of a particle or a system. Electron, before it has been measured, would be such a particle or system. The wave function psi is a variable quantity that describes a wave-like characteristics of a particle. But note that this is a complex quantity, meaning it has both real and imaginary component. And because of this, we can't really say what it represents literally. And physicists don't agree on its meaning either. What we do, however, is interpret its meaning. What we are talking about here is called Copenhagen interpretation. There are many others as well. Notice that the math does not say anything about the interpretation, and science does not say which interpretation is correct. That's why don't think of the animation that it literally represents the particle prior to measurement. However, the norm or a square of the wave function represents the probability density in 3D space of finding the electron in a certain location when we measure it. That is what represented in the animation. You might have noticed me saying before measurements quite a lot. Why? Well, the answer lies in the question, why does quantum superposition not happen on a macroscopic level? We can go back to our experiment and try to see the electrons. Let's put a tiny light source between the slits. When you do that, you find that some of them were indeed going through slit 1 and some through slit 2. But we no longer get the interference pattern now. Because when we observe, we break the quantum superposition due to interaction. This does not mean that it needs a conscious living thing to observe it, like you may have heard it from pseudoscience people. No, observation in physics is simply a non-reversible transfer of energy. You see, up until now we have been doing our experiment in complete dark. But when we do that outside, we never find an interference pattern, because the outer world has particles always interacting with the system. Quantum superposition does not only apply to the electron going through slit 1 or slit 2, but it applies to all quantum properties, like let's say electron spin. When you measure electrons' spin, you might get spin up or spin down 50% of the time. But when there is no measurements or interaction happening, the electron does not have an up spin, nor down spin, nor both, and nor neither. The electron would be in a quantum superposition of being spin up and down. And that does not mean up and down at the same time. And I cannot show you what that means in animations. This is what Schrödinger and Einstein did not like, nature being probabilistic. And to express that, they came up with a thought experiment of the cat in the box. So just like the atom in the box is in the quantum superposition of decayed and not decayed, the poisonous gas is in the superposition of being released and not released, and the cat is in superposition of being alive and dead. That does not mean that the cat is alive or dead. It's also not both, and it's also not neither. Hope you understand it now. So Schrödinger's and Einstein's argument was, does it make sense for the cat to be both alive and dead? No. So that's why quantum superposition is not real. But now from countless experiments, we know that the quantum superposition is real. It just does not apply to macroscopic level due to all the interactions. As long as you don't measure or observe a quantum system, quantum superposition is real. Wait, so why does it matter to us? If it only applies to microscopic world, if you don't and even can't observe it, does that have any significance for us? Consider an atom with a nucleus and an electron associated with it. What happens if another nucleus is brought nearby? Now, the electron faces multiple possibilities. It could stay around the first nucleus, move to the second nucleus, be near both, or avoid both entirely. However, none of these outcomes fully describe the situation. Instead, the electron enters a quantum superposition, where it simultaneously exists in the states associated with both nuclei. Even with a single nucleus, the electron isn't orbiting the nucleus in the classical sense. That's why the term orbital is used instead of orbit. The electron's presence is spread out in a quantum superposition around the nucleus, forming what we call a shell. When two nuclei are introduced, this quantum superposition of the electron between them creates a force that holds the nuclei together. This phenomena results in what we know as covalent bond. It's important to clarify that the electron isn't being shared between the nuclei in a literal sense. Rather, It exists in a quantum superposition state around both, and I can't show that in animation. Covalent bonds are fundamental to life as we know it. From water molecules to DNA, proteins, fats, and carbohydrates, everything essential to life relies on covalent bonds, which in turn depends on principles of quantum superposition. If you learn something new about quantum mechanics here, you will absolutely love to see how, as per Einstein, magnets might not be real, and they are definitely not what you think they are. Click on this video here and I will hopefully see you there. Thanks for watching.